Good afternoon, everyone. My name is Rajat Boni. I am one of the PMRF research scholar at IITSM Dharma, and I am one of the TA of this foundation engineering course, which is conducted by Professor Dilip Kumar Vaidya sir. And I have also 6 month teaching experience in Nptel as a TA, and my previous course was uh, ground improvement, which also conducted by Professor Dilip Kumar Vaidya sir. So today we are in week 11 of this foundation engineering course. Only one official weeks are remaining, week 12, and there is another extra one class, which is extra class, uh, which will be conducted on 14th April in same timing, 4 to 6. So be prepared for this. And today we will discuss the further uh, topic of this foundation engineering, which is brace cut or deep excavation. It is related to the sheet pile and anchor sheet pile. So today we discuss this topic, and after that we discuss the dynamics of the foundation, machine foundation, or introduction of the machine foundation. So, and then if time permits, we try to solve previous year assignment questions. If not, I will share the previous year question and solution to my Google Drive. And one or two point uh, I want to discuss here that this session is recorded and it will be uploaded my YouTube channel. If you anything miss, you can go through later uh, on my YouTube channel, and then also whatever I am discussing, it will materials. It will be uploaded on my Google Drive. So don't worry about this. And if and one thing more that if there is any discrepancy in network, so please stay on the line. I will try to solve this problem and rejoin again the meeting. So let's start our today's session. In so before starting our discussion, we already covered the uh, what is the purpose of that foundation engineering, what are the different types of foundation. Then we study the shallow foundation. There is a different types of shallow foundation. We also study. Then we come to deep foundation and also study the different types of deep foundation, mostly the pile foundation and group of pile foundation. Then we cover the sheet pile and anchor pile. So one or two, I think in group from pile group to sheet pile and anchor pile, I there is remaining the problems. I will solve it in our extra session, so don't worry. And today we start the base cut and deep excavation. So I am sharing my screen. Please wait. I think it is visible to everyone. Also, I am audible to everyone. So start with today's session, that is week 11, lecture number 51. In lecture number 51, we mostly discuss about the deep excavation. So what are the requirements for this deep excavation and why we need this arrangement? And then we try to solve regarding to this deep one problem regarding to this deep excavation. Um, and then we move on to the dynamics of the foundation and mostly the machine foundation. So, so we know that an unsupported curve in C5 soil, the pressure distribution at a depth of the pressure distribution at a depth of h is written as sigma 3, which is a horizontal pressure for active earth uh, case, active earth pressure case, and sigma 1 is the vertical pressure, and c is the cohesion. So we return as sigma 3 is equal to sigma 1 into 1 minus sine phi divided by 1 plus sine phi minus 2c root over 1 minus sine phi by 1 plus sine phi. So if you simplify this, so 1 by sine phi by 1 plus sine phi as a earth pressure, active earth pressure coefficient K, then the equation is sigma 1, which is nothing but the particle uh, effective stress into Ka, active earth pressure coefficient minus 2c into by Ka. So at the ground surface, when the H is equal to 0, so we know that if H is equal to 0, there is no effective stress, vertical effective stress. So sigma 1 is 0. So there are only remaining minus 2c root over k. So in the sign is negative, so we consider that it is act as a tension in the soil. Due to this tension, there may be crack on the soil due to the active earth pressure condition in C5 soil. So, so the theoretical depth of the crack ST can be determined by recognizing that at the bottom of the crack sigma 3 is equal to 0. So the this depth of crack, which is called HT, is find out when the at a depth where the sigma 3, that means horizontal effective stress, is 0. So if you put sigma 3 is equal to 0, our and rearrange uh, the equation and find the HT. The HT is equal to, that is height of the depth of the tension crack is equal to the 2c divided by gamma into root over k. So our height is 2c divided by gamma into root over k is tension k. And if in case of the deep excavation, the unsupported curve in seafloor soil is the two times of the tension curve, because if we see the pressure diagram, the pressure is linearly increasing from the top to bottom. In top, there is a negative pressure, and after a tension came there is a positive pressure. So this at a depth of tension cake, above the tension cake, this pressure, negative pressure, that is tension, is neutralized by after a certain depth, which is equal to same equal to the tension cake. So if by this concept we say that up to these two times of a tension cake, there is no need any support to for this type of soil, because there is no pressure which is coming from the soil, because it is neutralized. This tension is neutralized by this compression, so there is no need to any support. So this depth from the top surface to this two times of this tension crack is known as unsupported depth, and which is equal to the force C divided by gamma into root over K. So which is also called HC. Then moving forward, here it is said that shallow excavation can be made without supporting the surrounding material if there is an adequate space to establish slope at which the material can stand. The steep slope that can be used in a given locality are best determined by experience. Many building sites extended to the edge of the property line. Under these circumstances, the side of the excavation have to be made vertical and must be usual by supported by bracing. So it is said that we can, if for shallow excavation, if you need to excavate the ground for any purpose like for foundation, or construction of the foundation, or collecting sample, then for shallow excavation, there is no need any support for supporting the surrounding material. Because in our previous concept that in C5 soil the unsupported depth is force C divided by gamma root over K. So up to if our shallow depth is within this force C divided by gamma into root over K, then there is no need to any support. But in if it is uh, if we excavate further, then there is a need support. But for this case, we do one thing that we excavate in a sloping manner. That means like this. So for this case also, we don't need any support for excavating deep excavation. But sometimes there is many building sites are present, and also our site is the uh, at the edge of the property line. So for this case, or due to the confinement of the area, we don't use the steep slope or slope for to excavate the excavation. So for this, we use vertical cuts like this or vertical excavation. And to support this vertical excavation, we sometimes use, we mostly use the bracing to which is counteract this vertical uh, sides of this excavation like this. And our today we discuss more about these bracings and what how much load is take this bracing and how to find it. We now discuss. So there is two types of bracing we use. One is steel sheet piles, and another one using the H piles. The the common method of bracing the sites when the depth of the excavation does not exceed 3 meter. So this type of bracing is used when the depth of excavation is not exceed 3 meter. So the figure A is for steel sheet piles using basing using the steel sheet pile, and figure B is for basing using the H piles. So it is said that the cross section through typical basing in deep excavation are shown in this figure. Then the practice is to drive the practice is to drive vertical timber planks known as shifting along the side of the excavation. So it is said that the practice to drive vertical timber planks is known as the sheeting along the side of the excavation. The sheeting is held in a place by means of horizontal beams called wells, and that in turns commonly supported by strut extending from the side to side of the excavation. So first we drive a sheet piles along the vertical walls of this excavation. After that, we construct the horizontal beam along this vertical sheet piles throughout our cross section. That means, in if you see the figure, this vertical beams, which is called waves, this dotted black dot is called wells, which is perpendicular to our surface of the sheet. So, which is called wells, and these wells or horizontal beams is also supported by a strut extending from the side to side excavation. That means this is called strut, which is also supported, which is also which support the this wells. So moving forward further, it is said that when the is excavation depth is exceed about 5 to 6 meter, the use of vertical timber sheeting will become uneconomical. According to one procedure, steel sheet piles are used around the boundary of the excavation. As the soil is removed from the enclosure, wells and strut are inserted. The wells are commonly of steel and the strut may be steel or wood. The process continues until the excavation is completed. So this process is continued throughout the excavation. So it is said that if our depth is less than 3 meter, then we use timber sheet. But if your depth is exceed 5 to 6 meter, then we use the steel sheet piles instead of timber sheeting, and we use the steel wells uh, for most commonly use the steel wells, and the start may be steel or wood. And here the pictures are given, which is not clear here. In later, I will show you that this picture. It is see there is different arrangement of these joints. These joints for one is for steel sheet piles, another one for H pipe. So it is said that it is shown here that for steel sheet piles, first we insert the sheet piles, then there is then we attach the or connect the wells. After that, from these wells, there is one at a particular perpendicular direction. We connect the star, which is also connect. We also join of the opposite side of other sheet pipe. So similar way, there we use instead of sheet pipe, we use H pipe, and to support the vertical walls of this excavation. And after that, we use the wells, and similar way we also use the strap. Now, for the design of this strut bracing brace cards, we first for different types of soil, we first assume the pressure diagram of these different types of soil to estimate the force acting horizontal force acting on this strut. So it is said that for sand, we assume that uniform pressure distribution diagram throughout the depth of the excavation, and the pressure is assumed uh, is assumed as 0.65 gamma h tan square 45 degree plus 5 by 5 by 2. So you can see that it is nothing but the 60% of the horizontal earth pressure, horizontal effective earth pressure. So we know that the horizontal effective earth pressure is gamma h into kp or k. So if you multiply it by 60%, 65%, which is become uh, 0.65 gamma h K or Kp. If you write Kp as a tan square 45 degree minus 5 by 2, or K is tan square minus 45 by 2, and Kp is tan square 45 degree plus 5 by 2, then it is similar to this equation. This comes similar to this equation. Then there is for clay, there is we use two types of clay, or two types of clay, different pressure diagram we use. So it is said that if the stability number, which is equal to the gamma h by c, is less than equal to 4, then it is called the stiff Fisher clay. And if the stability number, that is gamma h by c, is greater than 4, we call it as a soft to medium clay. And for this stiff clay, the pressure diagram is like this trapezoidal shape, where at a depth of point two depth of from the ground surface, at a depth of up to a depth of point 2 or 25% of the depth of excavation, the pressure is linearly increasing. After that, the pressure remains constant up to a depth of zero point 0.5 h. Again, after a depth of zero point 0.5 h, the pressure again linearly reducing up to a depth of 0.25 h. And this width of this pressure diagram is 20% of the vertical stress, we can say 20 to 40% of the vertical stress, which is equal to the zero point 0.2 gamma h to zero point 0.4 gamma h. Then for soft to medium clay, a soft to medium clay, this pressure diagram is from the ground surface up to a depth of 0.25 h. The pressure diagram is linearly increasing, and after 0.25 h, uh, uh, up to the depth of h, the pressure is remain constant, and the width of this pressure diagram is uh, gamma h minus 4c. So this pressure diagram is mostly useful to this pressure diagram is mostly useful to find out the horizontal force act on this strap, or acting on this strap. So for different types of soil, we consider or assume the different pressure diagram for our convenience to solve or design the this brace or strap. So then now we discuss the design procedure of this strut or brace cut. So you see that our brace cut for a deep excavation is like this. After a certain interval, we place this horizontal strut to support this vertical wall of this brace cut. So along this, we draw the pressure diagram for different types of soil. This is for sand. This is for stiff clay. This is for soft to medium clay. So this we have to find out force at this joint, at this joint, at this joint, at this joint, and at this joint. So we consider this joint is a hinge joint. So moment will not transfer to this joint. Only horizontal force will transfer. So due to this hinge joint, we particularly divide uh, uh, this point according to hinge joint, like this here, like here, like here. So after that, uh, we calculate the force according to the joint. That means we apply the equilibrium equation to find out the force. That means we divide here force one, here, here. So we divide this pressure diagram according to this joint. That means for sand, which is uniform, we divide according to the joint like this. We say this is A, this is B, this is C. And we, due to the hinge joint, there is a pressure force act and FA1. Here also force act FA2. Here it is for B joint FAB1. Here also FB2, and here it is FC. So FC. So we have to use the equilibrium equation, that is the force acting on this pressure diagram up to this is, which is equal to the FA1 for this diagram, and force acting on this diagram, which is equal to the summation of the FA2 plus FB1. And after that, and also use the moment equation at any of this joint, and we find out the each of the uh, force at the joint. Similarly, we find out for this also. After finding that for joint A, the total force is FA1 plus FA2. Similarly, for joint B, the total force is FB1 plus FB2, and for joint C, which is same as the FC. So similar way, we also divide this pressure diagram for stiff clay and for soft clay also. So for stiff clay, this is like this, like like this. So sorry, here it is. Somewhere here it is FA1. Here it is FA1, FA2. Here it is FB1. Here it is FB2. Or somewhere here it is FC. Like this, we find out and solve this equilibrium equation and find out this FAFPSC for this type of problem. For stiff clay, similar way, we also divide the soft clay also. So here FA1, FA2 here act, here FA1, FB2 act, here FC act. So solve and find the solution. Now, moving forward, now there is the now we have to find out the factor of safety against this brace cut. Whether it is safe to excavate or use this brace cut or not, we have to find out. So there is two cases we consider. So in case one, it is said that when the clay below the cart is homogeneous, at least up to a depth equal to zero point 0.7 B, where B is the width of the cart. So it is said that we have to find out the factor of safety when at the below the excavation the soil is homogeneous and which is clay, and up to a depth of at least up to a depth homogeneous at least up to a depth of zero point 0.7 times of B, or B is here the width of the excavation or cut. And why we use this factor of safety? If you see this diagram, from the side of this wall, there is heavy pressure acting vertical pressure acting at the level of this bottom level of this car. Due to this heavy pressure which is coming like this way here, uh, heaving may occur at the bottom of the excavation. So to avoid this heaving, we use factor of safety and limit our design. So why it is happen? So if you see that due to this excavation, there is no material is present. So there is nothing to nothing which is uh, act pressure at the bottom of the cut. But at the side wall, side of the cut, there is present soil mass, and which is as a apply the vertical effective stress at the bottom of the bottom level or self weight at the bottom level. Due to the self weight, that soil which is at the bottom of the cut try to uh, maintain the equilibrium, try to occur or process the heaving, and due to this heaving sometimes this deep cut is may fail. So to find out this factor of safety, first you have to find out the force acting, total load or force acting at the side of the cut. So it is said that the anchor load block of the soil A, B, C, D in figure of width B assumed at the level of the bottom of the cut per unit length may be expressed as. So here we use here we use or consider on one anchor load block which is named as ABCD, and the width of this anchor block wall is equal to the V1 root 2, where V1 is the half of the width of the cut, and this B1 root 2 we term as the B bar. So we consider this ABCD as a mass block, and the weight of this block is unit weight plus into volume. So volume is here is unit is gamma, volume is here is h, depth into width b bar into length. Length is where we consider unit length. So here it is a per unit length. So consider 1 into 1. So total weight of this block is gamma h into b bar. Again, due to this weight of the block, this block is tried to move downward, and there is a zone, a friction zone created along this block, and this which is this friction force, which is nothing is equal to the this friction force is occurred due to the cohesion of the soil, and which is equal to the C into cohesion of the soil into depth of this block. So, but this force weight of the blocks is acting downward, and the friction force act opposite direction of the movement of the block. That means upward. So total net force is Q is equal to gamma H bar H B bar minus C into H. Now we due to the Tarjagi bearing capacity for homogeneous clay, we know that the bearing capacity of the soil is point CLC, which is equal to 5.7 C. So, for safety purpose, this bearing capacity of the soil should be greater than of this net Q. That means uh, greater than this net pressure, which is equal to the Q, which is further equal to the Q capital Q by V bar. If you return simplify this equation, which is equal to the H into gamma minus C by V bar. So our pressure should be, this ultimate bearing capacity should be greater than this Q net pressure, which is generated due to the movement of this anchor load block, and if it is greater than this Q, it will be safe from creating heat on the at the bottom of the cut. So, if we then our factor of safety is equal to the Q ultimate divided by Q. So put all this equation, that is 5.7 C divided by H gamma into gamma minus C by B bar. So this is the our factor of safety of for this type of condition problem. So you see that QU by small q. QU is the 5.7 C and Q is the H into gamma whole into gamma minus C by B bar. Now if we put this B bar value, which is equal to the zero point 0.7 times of the width of the cut, that is B, then we further simplify this equation as a factor of safety as 5.7 C divided by gamma H whole into gamma minus C by 0.7 V, and it is due to uh, found that the width V bar cannot exceed 0.7 times of B. So we substitute this B bar as a 0 0.7 times B. Now case 2, where there is the presence of a hash atom uh, below the brace cut, but this hash atom is depth which is less than zero point 0.7 times zero point 0.7 times of width of this cut. So we just replace this B bar as as the as a D, which is nothing but the depth of the hash atom from the bottom of the cuts. So we modified the equation as a 0.75 C divided by H whole into gamma minus C divided by D. And if we further simplify, that means if you consider that C by D is less than, much more less than equal to 1, then we rewrite this equation as 0.7 C divided by gamma H. Further, if we take this C below, then it is become 0.75 gamma H by C. And we know that gamma H by C is nothing but the stability number. which is N, which is represented as NS, and our modified equation is factor of safety. A modified factor of safety is 0.75. Sorry, 5.7 uh, divided by stability number. And it is said that a smaller movement with smaller value of stability number. So there is a smaller movement occur of this bottom of the cut when the stability number is more. Now moving forward, which is lecture number 52. So in 52, we solved one. Now we solve one problem regarding to this concept. So first, is wait. So first, understand the problem. So it is said that a brace sheet pile for an open cutter in soft to medium clay is illustrated in figure. So figure is shown as a brace cut uh, arrangement. Studs are placed longitudinally at 4 meter center to center, and the sheet piles are pinned or hinged at the stud level B and C. Draw the lateral earth pressure diagram for the sheet brace sheet pile system and determine the load on the stud A, B, C, and D. So it is said that the pin and hinge joint are present at uh, B and C only. So we divide our pressure diagram according to the B and C point. Then it is said that the studs are placed longitudinally at 4 meter. That means our length of this wells beam is 4 meter center to center, which is in figure, which is perpendicular to this diagram. Then the properties of clay are given here that it is soft to medium clay. So our pressure diagram should be like that, and total depth of this cut is given 12 meter. So 0.25 times of 12 is equal to 3 meter. So this from here to here it is 3 meter, and here to here it is 9 meter. Then it is said that QU is given, that is undrained shear strength is given. So we know that cohesion of the soil is half of this undrained shear strength. So it is become 96 divided by 2 becomes 48 kilonewton per meter square. So now we move to the solution page. So here it is said given three types of pressure diagram. So our problems is related to this pressure diagram, and the width of this pressure diagram is given gamma A into H minus 4 into C. which is equal to the gamma is 17.29 and H is 12 minus 4 times of C. C is the question which is find out about 48. So we calculate it and find the answer, and it is become which is equal to 15.48. So the width of this diagram is 15.48. Now try to divide this pressure diagram according to B and C, which is at a depth of 4.5 meter from the ground surface, and also another is 7.5 meter from the ground surface. So our pressure diagram is like this. This is 0.15, sorry, 1.5 meter. This is 3 meter. Sorry. Up to here it is 3 meter. Up to here is 1.5 meter. Up to here, which is point A, is 1.5 meter. Up to here it is 3 meter. Then again from 3. So it is FA, it is FB1. After that, 3 meter, FB2, FC1. Last uh, 6 last 4.5 meter. The last 4.5 meter passage diagram is it is FD and it is FC1. Here to here it is 3 meter. Here to here it is 1.5 meter. And we know that it is 15 point width of this is 15.48. Also it is 15.48. Here also it is 15.48. Now try to solve uh, this apply equilibrium equation for each of these pressure diagram. And first, we know that this area of this pressure diagram give the total force acting on it, which is equal to the summation of first diagram, summation of Fa plus Fb1 for and one equation is we find after applying moment of this point, we know that this point moment is 0. We find out Fa, and then we if we subtract total load from total load Fa to find out Fb1. For this diagram, this pressure diagram is uniform, so Fp1 is equal to Fc1, Fb2 is equal to Fc1, and this is equal to the half of this load of this diagram or area of this diagram. Then here for this diagram, We apply total force is the summation of the FD plus FC2, 18 FC2. And if you apply moment about this point, you first find out the FD, and if you subtract FD from the total force, we find out the FC2. So by this way, we solve this problem. So now I moving to this solution page. So please stay on the line. I am sharing another. Yeah, I think it is visible to everyone. Solution. So you see that we first divide this special diagram here, here, here. So for figure one, we take moment about this point B. So which is equal to uh, which is equal to area of this diagram into multiply by the CG of this diagram according to the point B. So area of this diagram is half into, for triangular part it is half into 15.48 into 3, 3 is height and into 4, and the CG of this first upper triangular part is 1.5 plus 3 into 3, 1 by 3 plus 1.5 into 1.5 is the bottom part into 15.48 into 4 into 1.5 by 2, which is equal to the FA into 3. From here it is distance is 3. So you see that here to here it is 3, here to here it is 1.5, here to here it is 3 meter. So I think it is for this it is 15.48 into 4 into 1.5. 4 is the longitudinal spacing, uh, and the CG is half of this 1.5, and area of this diagram is 15.48, half of 15.48, or we can say area of this triangle into 4 into CG is 1.5 plus 3 into 1 by 3, and FA is equal to FA we don't know, but from here to here it is 3 meter. So put all this value, solve this equation, and Fa becomes 100.6 kilometer. Now, now Fa plus Fb1 is equal to the area of this diagram. So if we put all this value and solve it, the Fb1, then it is become 85.2. Now for figure 2, the FA and FB2 and FC1 is equal, and which is equal to the half of the special track area of half of the area of the special diagram, and which is become 92.9. So FA, FB1, FB2, FC1 we find, and the last part is FC2 and FD. So for finding out the FC2 and FD, we take the moment about the point C. So the total moment of this area is total area into half of point 4.5, and the moment according to FD is 3 into the force FD. Uh, and solve this, and FD becomes 209 kilonewton. After that, we know that the total area is force total area is equal to the summation of the FC2 plus FD. If you put FD value and subtract from the total uh, force, it is become total area. We find out FC, which is equal to 69.6. Now FB and FC is equal to FC is equal to FC1 plus FC2. FB is equal to FB1 and FC2. So by this way, we solve all these forces. So I think it is okay to everyone. In our later part of this our today's session, we try to solve, if time permits, we try to solve another types of problems similar to this topic. Now move to our lectures again. I think it is visible to everyone. So lecture number 52 of this 11th week also completed. Now move to lecture number 53. So before moving to lecture number 53, we now take a small break. After that, we start the lecture number 53. And lecture number 53, we actually start the discussion about the machine foundation, or you can say dynamics of the foundation due to the machine vibration of the machine foundation. So now we take a small break. After that, we again join. Hello. So welcome back to this session again. So let's start our remaining our session and try to complete the remaining part of today's session. So machine foundation is act on the principle of the dynamics of the foundation, and the dynamics is depends on the inertia force of the body, and which is mostly time dependent. So here the basic difference is shown of this static problem and dynamic problem. So we see that there is one block is rest on a surface, and below the block the friction is F. So in static problem, the force F, which is used to move the block, is equal to the nothing but the friction force mu into M. But in dynamic equilibrium problem, there is extra force is coming to equilibrium this force Ft along with this friction force, which is nothing but the inertia force, which is equal to the m into mass of the body into acceleration of the body due to this applied force. So you see that if body move here in this direction, there is a force act, inertia force act at the opposite direction, which is equal to the body acceleration into mass of the body. And we retain as the equilibrium equation is inertia force plus friction force at the bottom and into equal to the external force which is applied to move for movement of the body. Now here it is shown different types of force, which is so one is periodic, another is random, another is transient force. So periodic force is that type of force which is periodic motion is that type of motion. After a certain period of certain times, the amplitude, acceleration, magnitude, whatever it is repeat. So you see that after a cycle, that means one cycle is. So you see that this portion or this diagram is repeat after this point. So you see that here to here is complete one cycle. So after a certain point, this same motion is repeated. So you can see that we can call it as a periodic motion. But in random case, there is nothing repeating or repetition. So it randomly the motion is happening. We cannot predict the future motion. So like this, we cannot predict whatever the motion, how it is, we cannot predict. In transient case, is that the motion after a certain period of time is vanished or the motion try to get resolved or dissolved. So this type of motion is called transient motion. So source of dynamic loads. So there is different types of source to produce the dynamic load. So one is operation mode machine. So you know that machine is due to when we uh, machine when we operate the machine due to the operation there is a frequency is generated in the machine. Due to this frequency or something called due to this rotating mass. Most of the machine inside the machine there is a rotating mass, and due to this rotating mass, their frequency created, and this due to this frequency, dynamic motion of the foundation is created, and most of these motions are periodic. That means it is repeated after a particular period of time or particular cycle. Again, vehicle movement. Due to the vehicle movement, there is also create the dynamic loads. Then pile driving. Due to this pile driving, uh, there is also create the dynamic loads. Uh, then blasting operation, which is similar to the earthquake load. Then wave motion like this, like seawater motion, or so, which is create the dynamic load. Earthquake we also use earthquake load. Also, we call the dynamic loads. And here again, these pictures are again elaborated. So this is for rotating machine. This diagram is for rotating machine. This diagram is also for rotating machine, but idealized. Idealized means this portion is neglected, and we idealize the motion as a sinusoidal motion. This is for impact machinery generated mostly for pile driving or heavy tamping or blasting. This type of motion is generated. Now types of vibration. There are two types of vibration: free vibration and forced vibration. So again, in free vibration there is two types: undamped free vibration and damped free vibration. And in forced vibration there is again undamped forced vibration and damped forced vibration. So free vibration is in that type of motion which is occur freely without helping any external force. But in nature, there is nothing called free vibration. To produce a free vibration, initial force are required to generate some free vibration. After a particular time, if this motion is called free vibration, if the initial force becomes zero, and there is damped and undamped vibration. And damped vibration, undamped vibration is that there is if the motion is created, if motion is continuously go on, there is nothing in, to stop this motion, and it is continuously go on as infinite time, uh, until infinite time. So or we can say there is nothing to absorb the energy of this motion. So this motion is continuously go on. But and damped vibration is that type of vibration is the energy of this motion is reduced due to the presence of uh, due to the material behavior, or we can say the or surrounding material, or sometimes the internal property of the material. So this is called damped vibration. Due to this damped vibration, after a certain period of time, uh, the motion get reduced or dissolve. So damping is a material property, and there is nothing called undamped vibration. Some damping is present on any type of material. So in mathematical way, we now represent this each of these vibration. So undamped vibration we represent by using, or vibration we represent by using in if you use spring, by using spring stiffness we mostly represent. Uh, for damping, we use the dashpot to represent the damped vibration. So first one is undamped free vibration. So the mathematical equation for undamped free vibration is mu double dot plus k u is equal to 0. So and this is represented like this way. If there is a spring and there is a block which is attached to a spring which stiffness is k and the motion is like this u. And here u double dot is the acceleration, m is the mass, so this is inertia force, k is the stiffness, u is the motion displacement, so this is the stiffness force, and here if it is the free vibration, so this is equal to 0. Now, damped free vibration, the mathematical representation is mu double dot plus cu dot plus ku is equal to 0. And it is represented as the dashpot, spring dashpot. So here it is spring, here it is dashpot, and which is attached to a mass m. And the dashpot coefficient is represented as c, a spring coefficient is represented as k, and the motion is u, it is free. Now forced undamped forced vibration. So the mathematical equation is mu double dot plus ku. Sorry, no, what is the ku equal to f, which is dependent on time. F this means force, which is dependent on time. So there is external force applied to create the vibration, and it is represented as a diagram like this. We apply Ft, which is k. Now, damped force vibration, the mathematical equation is mu double dot plus ku plus cu dot equal to ft. Cu dot nothing but u dot nothing but the velocity. C is the damping coefficient or dash force coefficient into equal to ft. Ft is the external force, so it is represented as spring dash force into mass applied force ft. Okay, spring coefficient, C is the dashpot coefficient. So these are the difference of the undamped free vibration, damped free vibration, undamped force vibration, damped force vibration. Now moving towards the next lesson, and here is the representation of the damped force vibration in this figure. So there is four types of four types of uh, vibration or dynamic force, and which is mostly depend on the damping of the nature, and it is categorized as undamped and damped. So if undamped case, the motion never fails, it is continuous go on like this as an infinite time, up to infinite time. But in damping, if the damping is passive, due to the damping, the energy is absorbed, of motion energy is absorbed, and it is after a certain period of time, it is reduced. So the motion is like that. After sometimes it is vanished, and it is called transient motion due to the dissolve of this motion, and this is called damped by system. So there is we generally categorize as a damping and undamping motion. Moving forward, there is a given the solution of this uh, free vibration in undamping case. So you can see that this solution is represented as cos and sine, and it is equal to the u any displacement or motion at a particular time is equal to the u naught is the maximum amplitude of this motion into cos root over k m t k root over k by m into whole into t plus u naught divided by root over k by m sine into root over k by m into t, and this is if you consider u naught as a u cos alpha and u naught by root over k by m as a u sin alpha, we further simplify this equation as a u is equal to capital U cos omega t plus alpha, where omega is equal to root over k by m. For undamped free vibration, this omega is nothing but the natural angular frequency of the system. So this is called natural angular frequency of the motion, and this is only get this is only get by this free undamped condition. Now free damped condition, there is the equation is mu double dot plus cu plus ku equal to 0, and the system is represented as like this, and it is also called the transient motion. Then this solution of this equation we discuss in our later session. So now we move on to the lecture number 54. So in lecture number 54, the solution is given directly given the solution of this force damped vibration. So the force damped vibration is equation is represented at mu double dot plus ku is equal to ft, and where motion of this equation u is represented as equal to f naught by k divided by 1 minus omega square by omega n square into sine omega t. So how it is come? If you if you represent this ft as a constant force, some constant force of constant sinusoidal force, then we written as ft is equal to f naught sine omega t, where omega is the operating frequency and omega is the natural frequency, which is equal to the root over k by m. So ft is the maximum amplitude of this forcing of this force, and and if you represent this portion in a graph which is looking like this, and this factor which is called 1 by 1 minus omega square by omega n is represented as magnification factor. So magnification factor is nothing but 1 by 1 minus omega square by omega n. So you put this omega by omega n whole square as 0, then this is equal to 1. Start graph is start for 1. After a certain ratio if equal to this omega omega ratio is equal to 1, then this magnification become infinity. So from 0 to 1 ratio, if the ratio omega by omega n, frequency ratio, which is also represented by sometimes neta, is if we in between 0 to 1, then the magnification factor always in positive, uh, always positive. But if it is greater than 1, then it is always negative. But if it is equal to 1, then this magnification factor is equal to infinity. And it is the representation of the resonance. So resonance is the phenomena when the operating frequency matches the frequency of the uh, operating frequency of the force is matches the natural frequency of the body. So if both are same, then resonance happens, and due to this resonance, the frequency amplitude get maximum. And sometimes, if undamped condition, sometimes it is infinity in mathematical way. So which is very dangerous for any system, because due to this maximum amplitude the system may get failed. So our design should be like that. It should be within the natural, in between the natural, either in between natural frequency or greater than the natural frequency. Don't it should not be matched with the natural frequency. And this graph is for undamped force vibration for to find out the magnification factor. Now there is the introduction of machine foundation. So in machine foundation there is a rotating mass always present. Due to this rotating mass, vibration is generated. If there is a single mass is rotated, then the force generated due to this single mass is me, which is the mass of the rotating mass, into E. E is the radius of this rotating mass. Radius of this rotation, and omega is the frequency, angular frequency generated due to this rotation. So the force generated due to this rotating mass is equal to the Q naught is equal to the me into E into omega square. Then there is a two counter rotating mass. So due to this two counter rotating mass, different types of frequency you can generate. So we can see that when this rotating this when this mass is rotated, they exert the force in outward direction, always in outward direction, like this. So when the mass is present there, the force is like this. When it is away, the force is like this. So when so by this concept we say that when the mass two mass is come closer, they neutral to each other. When two mass air from each other, they generate a motion. So and this motion is nothing but generate a periodic motion like this. So when the two masses come closer, then there is a no motion. If two mass air from each other, so there is creating a motion. After some time, give a peak value. After some time, it is again reducing and arc as in opposite direction. then again given peak value, and work is then again it is reducing. So it is generate a harmonic motion. Now, due to this two counter rotating mass, we generate the vertical vibration, torsional vibration, rocking vibration. So when this rotating mass is of this part and this part are in same direction, that means we see that the mass is here, here is similar to here and here, then it is generate only vertical movement, vibrate only in vertical direction. When this mass of this side is opposite to this side, then it is generate. That means due to this rotation of this mass, it is, you see that, you see that due to this rotation, this part, you consider this line, due to this part, they rotate. One part is rotate here, one part also rotate here. Similar way, this will also rotate here, this is also rotate here. So only vertical direction motion is created. But for this case, second case, the torsion case, one mass is rotated in this way, and the mass is rotated in this way. And so this motioner is opposite in direction. Due to this, torsion is created in this direction. In rocking motion, the mass is created in downward for this direction. In masses rotation is carried in downward direction. For this second portion, mass is created, rotation is created in upward direction. So due to this, rocking phenomena is happen, and this motion is called rocking motion. So here it is clearly shown by the picture. See that when the vibration in vertical direction, or we can say the block is block motion in vertical direction. This is the vertical vibration. When the block motion rotate along the vertical axis, then it is called torsional motion. When the block is moved along the longitudinal direction, it is called longitudinal vibration. When this block is rotated along the longitudinal direction, it is called rocking vibration. When the rock is movement is along the horizontal direction, it is called horizontal vibration. When the rock movement is according to the horizontal axis, then it is called rocking motion also, or sometimes it is called pitching motion. Now, here different types of dynamic equation are given for different types of motion. So for vertical motion, the equation is m z double dot plus kz is equal to f zt, where z is the motion in the vertical direction, and for horizontal direction it is m x double dot plus kx k into x is ft. But when we use this equation, dynamic equation for rocking and torsional motion, instead of mass, we use the mass moment of inertia. Instead of horizontal or vertical motion, we use the rotation along this for this rocking and torsional motion. So this are the mass moment inertia. I is the mass moment inertia. Psi is and theta is the uh, angular motion or angular displacement rotation for occur due to this rocking and rotational motion. Now, so here it is said that Z is the vertical displacement, X is the horizontal displacement, and psi is the angle of rotation along the horizontal axis due to the rocking. Theta is the angle of rotation around the vertical axis due to the torsion. So due to these different types of motion, different types of stiffness are created. So for vertical motion, the stiffness is equal to the 4gr divided by 1 minus mu, where g is the shear modulus of the foundation, r is the radius of the foundation, mu is the Poisson's ratio. For stiffness for the horizontal motion is 8gr divided by 2 minus mu. For um, uh, rocking stiffness, for rocking motion, the stiffness is 8g r cube divided by 3 into 1 minus mu. For torsional motion, the stiffness is 16 in g r cube divided by 3 into 1 minus mu. And this stiffness is find out for horizontal motion, it is find out, vertical motion is find out fz by z. For it is horizontal, it is find out fx by x. And for rocking, it is find out m rocking divided by psi. And for torsion, it is find out torque divided by theta. So by this equation, we easily find out the stiffness of the foundation. Now moving towards the next slide, which is the forced free vib, the forced damped vibration. And this is the equation for mathematical equation for forced damped vibration, which is equal to mu double dot plus cu dot plus ku is equal to ft. So this ft, that means the applied dynamic force, we represent in two ways. One is constant force amplitude, another one is rotating mass system or frequency dependent force amplitude. That means this in second case, this force is dependent on the frequency, and in first case, the force is a constant amplitude force. So for these two types of acting force, the equation also different. So first we find out for the constant force, the solution of this equation when we using the constant force is U is equal to F naught by K is the stiffness of the system. F naught is the constant force amplitude divided by 1 minus divided by root over uh, 1 minus omega square by omega square whole square plus 2d, which is damping ratio, which is nothing but equal to the damping coefficient of the system divided by critical damping, and this is find out by the undamped free vibration uh, into omega by omega n uh, whole square. So if it is when it is a constant force amplitude, the magnification factor by magnification factor by efficiency ratio graph is looking like this, and you see that this graph is start from 1 when it is when there is a frequency ratio is less than 1, and after it is reaching to 1, we reach the maximum magnification magnification factor we get, and this is occur due to the resonance of the system. If damping is zero, this graph uh, in upward direction may extend up to infinity, and after if the frequency ratio, this magnification get reduced and it is below 1. So by this equation we easily identify the motion by the magnification factor, and this magnification factor is equal to m is equal to for this motion is equal to 1 minus eta square whole square plus 2d neta whole square, and neta is nothing but the frequency ratio omega by omega n. So by this magnification factor, we easily describe the motion of the system for constant force amplitude. Now, if the our force is generally created due to the rotating mass system or if or if the force is frequency dependent amplitude, force amplitude is frequency dependent, then the magnification factor is changed and our equation become magnification factor become neta square divided by root over 1 minus neta square whole square plus 2d neta whole square. So for this case, there the uh, frequency ratio is come above at a numerator. So if we put the frequency ratio is zero, this we start waveform uh, zero, and uh, and if the frequency ratio is less than one, the values are less than one. The magnification ratio is less than one. But and if the frequency ratio is greater than one, then this magnification factor is reaching towards uh, 1 irrespective of the any damping ratio. Uh, but when it is approaching towards to 1, the this magnification factor is increasing, and it is get the maximum value uh, for any damping for a particular damping ratio, and if the damping ratio is 0, then this value becomes infinity. Now again we characterize this equation forced undamped forced damped vibration for different types of motions like vertical, horizontal and rocking and torsional motion, and this equation are similar to the previous equations, but one extra term is come, which is nothing but the damping uh, factor or coefficient into velocity. So there is a so moving towards the next slide. There is a it is shown the difference between the constant force system and rotating or frequency dependent force system. So in constant force system, the resonant or we can system frequency or operating frequency is equal to the omega n, into root over 1 minus d square. But in rotating or frequency dependent force system, the resonant frequency or operating frequency is equal to the omega n divided by 1 minus d square, where omega n is nothing but the natural angular frequency, which is equal to that root over k by m. D is the damping ratio, which is equal to the damping of the system divided by critical damping coefficient, and which is higher critical damping coefficient is equal to the 2 into root over k n. And for and the amplitude for constant force system uh, uh, is equal to the uh, f naught by k uh, whole divided by 1 minus omega square by omega square whole square plus 2d omega by omega n whole square whole uh, to the power half. And for rotating mass system, it is equal to the me divided by m into omega by omega n square whole divided by 1 minus omega square by omega n square whole square plus 2d omega by omega n whole square whole to the power half. And if we uh, and by this equation, if we derive it with respect to this frequency ratio, this omega by omega n, we get the maximum amplitude, which is for constant force system, which is equal to the f naught by k into 1 by 2d root over 1 minus d square. And for rotating mass system, which is equal to the me by m into 1 by 2d into root over 1 minus d square. So please remember this equation for solving the problems which we can directly apply to solve this the questions. So this difference solutions are very important to solve our assignment and also the exam problems. And this is for forced damped vibration. And again in force damped vibration, two parts: force, constant force amplitude, and rotating mass amplitude. Now moving to the lecture number 55, which is the last lecture of our session. Today's sessions, where again the same thing is repeating. So here uh, one two points are mentioned, that the requirements in machine foundation design, which is given by More 1985, are: no vibration damage is done to the structure on which machine is housed, nor to the adjacent structure. No damage is done to the machine. The performance of the machine or the adjacent machine is not impaired. Then excessive repair and maintenance cost for the machine, uh, adjacent machine and structure are not generated. Performance and health of the worker is not impaired. Health and comfort of people in the surrounding community is not impaired. So these are the guidelines we have to maintain for designing the machine foundation. So we have to design in such a way that due to the vibration there is no damage on the structure of the foundation. Also, no, there is no damage on the adjacent structure. So no damage. Also, there is also no damage on the machine. Also the performance of the machine is not impaired due to this vibration. Excessive repair and maintenance also not occur due to this vibration. Performance and health of the worker also not impaired due to this vibration. And health and comfort of the people in the surrounding community also not impaired due to this vibration. Now here one uh, plot is given based on displacement versus frequency. So it is said that if the frequency is below frequency is given in terms of and sorry, frequency is given in terms of CPM, cycle per minute, and displacement is given in terms of And it is said that if the displacement is in between 0.001 and also the frequency is in between the 1000 CPM, then it is best suitable to design any machine because there is not because the vibration is not noticeable to a person. But if in between, if the frequency is in between 1000 and to 2000 ccm, and also the displacement is in between 0.001 to 0.002 then there is barely noticeable vibration is barely noticeable to the person. Again, if you further increase the frequency uh, up to a certain up to 5000 and also the displacement up to 0.005 then easily noticeable vibration is easily noticeable to a person. And after that there is a troublesome after again if we increase the frequency then there is a troublesome of the vibration is troublesome to the person, and up to a certain limit we have to design this machine which is equal to amplitude of point up to amplitude of point 1 and the frequency is up to the 10,000 CPM. Beyond this, we cannot design because it is dangerous to the structure. Also, cause the severe effect to the person. Now, there is a different guidelines based on the uh, guidelines based on the different types of machine. So it is said that for reciprocating machine, the permissible amplitude is zero point 0.2 as per the IS 2974 part 1 for if you using hammer. For foundation block the amplitude is up to 2 for anvil. When you use hammer the amplitude is in between 1 to 3 when you are using rotating machine for speed less than 1500 rpm then the amplitude is should be within zero point 0.2 if the speed is uh, 1500 to 3000 then The permeable amplitude is in between zero point 0.4 to zero point 0.6 mm. If this amplitude is greater than 3000 rpm, then this amplitude is in between zero point 0.2 to zero point 0.3 mm. Now, there is a general guidelines to design the machine foundation. So it is said that design the machine foundation in such a way that natural frequency of the system be far away from the operating frequency. So we know that if the natural frequency, the operating frequency match the natural frequency, resonance occur. Due to the resonance, the amplitude is suddenly increased. The system amplitude of vibration amplitude is suddenly increased. Due to the increased amplitude of the motion, there is a severe effect or damage on the structure, which should be avoided during the design, and it avoided by keeping the operating frequency in as zero point 0.5 omega greater than equal to omega n greater than equal to 1.5 omega. So omega is the operating frequency and omega is the natural frequency. So we should either design our system below the natural frequency, which is equal to 1.5 times omega, and also or greater than the natural frequency, which is equal to the 0.5 times of omega. Further, if the operating frequency is very high, natural frequency should be less than zero point 0.5 omega, that is under uh, tuning for high frequency machine. And if the operating frequency is very low, natural frequency should be greater than 1.5 omega, that is overturning for a low frequency machine. So these are the guidelines we have to follow while designing the machine foundation for high frequency and low frequency. So for high frequency, the natural frequency should be less than zero point 0.5 omega. Omega is the operating frequency, and for low frequency, the natural frequency should be greater than 1.5 omega. So up to this, we now end our session. It is already 6:08. So we solve some problem in our next session, and I will share some assignment problem, previous assignment problem and solution in my Google Drive. Please go through it, and also this session is uploaded. So up to this, we end our session. So we will meet again in the next week. In the next week, there is a two class. One is Saturday, another one is Sunday. Sunday is will be happen. Extra class will be happen in Sunday. Um, Time is same 4 to 6. In next Sunday, next Sunday, uh, which is the 14th of April, and which will be our last class for this foundation engineering. So you try to solve some question regarding to this concept, and we will meet again in our next class, which is 13th of April. So till then, thank you everyone, and good night. We will meet again. So I am stopped here. Thank you.